Okay, folks, so in this problem we're considering a ball that's being thrown upwards at an initial upwards velocity of 40 feet per second from atop a building that is 75 feet tall. So just for fun, I've drawn a picture here. This picture isn't quite true to life for a lot of reasons. One is because the situation that I'm actually considering is a situation where the ball is just going upwards and then falling down like that. But that makes it a little bit hard to look at the graph, so I've elongated this parabolic arc just so we can get a better sense of what's happening. We're going to assume that the fellow 2 is of negligible height. So this is a function that would describe the height of the ball, S, we'll call S the height of the ball at any point in time, and time is measured in seconds here. So there's a lot of flaws to this model. Doesn't take into account air resistance, doesn't take into account a number of things. You know, it doesn't make sense for us to input negative values for t. This has a positive or zero domain, and it doesn't make sense to get h of t values that are negative. So the model only applies during the length of time that the ball is in the air. But it's still an interesting model. So you probably have some intuition for this. We expect that when we throw the ball upwards at 40 feet per second, we expect it to begin slowing down until a point where it has zero velocity because of the pull of gravity. So it's rising, and gravity slows it down to a point where it's actually momentarily, instantaneously at rest. But then it begins, as gravity takes over, it begins picking up negative velocity, falling, picking up speed, velocity as it does so, and striking the ground at a certain speed. So in this question, let's go ahead and find the average velocity between the first and second. Okay. So what we're going to see here, and let me just kind of give you a picture for what we're computing, we're going to find that after 1 second the ball has a certain height, and after 2 seconds the ball has a certain height, and our goal is to figure out, well, what was its average velocity over that time period. Okay. And so this amounts to, and we'll talk about this more in class, but this amounts to simply computing the slope of the secant line connecting these 2 points on this curve. So we're going to go ahead and compute the slope of this line right here. That's our goal. So let's go ahead and tackle this by looking at the definition of average velocity. So the average velocity between the first and second we could think of as, well, always average velocity is a change in height, which we're going to denote by s. So this delta symbol right here, this is symbol delta, means change in. So a change in height over a change in time. And it's important to just pause real quick and realize, yep, these are the correct units. We have the correct calculation here. Delta s is measured in feet, and delta t is measured in seconds. So the units on this quotient are feet per second, and that's what we expect to measure average velocity in. So how do we find delta s? Well, this is the change in s. So this would be how did the height change between this time and this time? So to do that, we're going to look at the height during the second, that would be this height right here, and we're going to subtract from it the height during the first second. So that height up here. So we're going to look at the difference between those two heights, and we're going to ask ourselves, over what period of time did that take place? Well, that happened between the second and first second, or over a change in time of 1. So let's go ahead and compute s of 2. So it would be negative 32 times 2 squared. Plug in a 2 there for the value of t. So times 2 squared plus 40 times 2 plus 75. So just to clarify, this quantity right here, s of 2, is this expression right here, minus s of 1, which would be negative 32 times 1 squared, plus, running into a problem here, plus 40 times 1 plus 75. I've got an extra parentheses in there. So just to clarify, s of 1, that is this expression right here, all over, and then we can compute 2 minus 1, we get 1 second. So crunching these numbers, I went ahead and already calculated them. This is 27 minus 83 all over 1, which gives us negative 56 over 1, or negative 56. Again, the units up here, this was our S, so the units up here were feet, and then per, so divided by, and then the units down here are second, or a negative 56 feet per second is our average velocity. So in answering the question on average, how fast did this ball fall during that 1 second interval, the answer is a negative 56, and that corresponds to the slope of this secant line. So we're going to now repeat this exercise, but we're going to do it more generally. So rather than saying find the average velocity during the first and second, we're going to find the average velocity between the t and t plus h seconds. Careful, I've got a and symbol in there, but that might look like a plus sign. So we're going to do this more generally. That is, we're going to be looking for the average velocity on the interval from t to t plus h. So in our last example, our interval was from 1 to 2. And so how would we look at this as being kind of the same structure? Well, we could think of this being 1, comma, and then how would we write this? Well, it would be 1 plus some little value h. Well, in this case, h would be 1 as well. So this interval that we dealt with last time could be more generalized to be an interval like t to t plus h. So our goal is to compute the average velocity between t and t plus h. That could be for any two time values. So that could be, for instance, right here, this could be the order pair t comma s of t. And then this time value right here, this would be the order pair t plus h comma s of t plus h. So the idea here is we're being more general, so this could be for any two pair of points over the life of this curve. So we're computing the average velocity over this interval. So just as we did before, we're going to say, well, that's the change in height, which we're denoting by s, over the change in time. So this delta notation should be starting to look a little familiar. So the change in height over the change in time. Well, how would we compute the change in height? Well, that would be s of t plus h minus s of t all over t plus h, this time value, minus the initial time value of t. So notice, if you look at these ordered pairs, this fits, right? Here was the ordered pair t comma s of t, and here we have s of t and t, and then here was the ordered pair t plus h, s of t plus h, and sure enough, there they are. Okay, in fact, let's go ahead and underline both of those. We'll underline that, and we'll underline that. So now let's actually start computing this. So I'm going to take this function, s of t. This is our function. Last time we plugged in a 2 for t, and we plugged in a 1 for t. This time we're going to be a little more abstract. In place of t, we're going to put t plus h. And if you have any questions about what I'm about to do, I'm going to attach a little video that should hopefully help to explain this a little bit better. But some of you may have seen this before. So I'm going to replace all of the t's in the height function with t plus h. So here we go. We get negative 32 times t plus h quantity squared plus 40 times t plus h plus our 75. So all of this expression here is the s of t plus h. Okay. Minus s of t, and s of t is just negative 32t squared plus 40t plus 75. I'm starting to get to the end. I think we can make it fit all over. And then here we have t plus h minus t. So, well, t minus t, those two terms add out, and so we're just left with an h there. Okay. Oh, and let me just clarify. In place of this s of t, what did I do? In place of this s of t, I put this expression here. Okay. So now at this point, And by the way, this is the hardest step, and so following this video, I'll attach a link that explains this step in a little bit more detail, or at least helps with computing t plus h. But after this, it sort of just becomes a basic algebra problem. We're going to clean up the numerator and then see if we can factor out and divide out any terms. So let's see what's happening here. So I'm going to FOIL this out, so we get negative 32 times t squared plus 2th plus h squared. And here I'll go ahead and distribute this, so we get plus 40t plus 40h plus 75. And then I'll distribute this negative sign to all of these terms. Make sure you distribute to all of them. So we get plus 32t squared minus 40t minus 75. And this is now all over h, or still all over h. Okay, so I'm going to take one more line. I better give myself a little more room. Distribute this negative 32. So this gives me negative 32t squared minus 64th minus 32 h squared. Fix that. Minus 32 h squared plus 40t plus 40h plus 75 plus 32t squared, careful, that's still plus, minus 40t minus 75 all over h. At this point I know I'm on the right track because I started out with a polynomial. And you're going to be doing this. Difference quotient. Again, this is called the difference quotient many times. And whenever the function that you're working with is a polynomial, you'll know that you're on the right track if all terms that don't have an h in them. So, for instance, this term doesn't have an h in them. You know that you're on the right track if all terms that don't have an h end up adding out. And we see that here. Sure enough, this negative 32t squared term adds out. Some would say cancel with that 32t squared. And let's see here, this 40t will add out with that 40t, and these add out as well. So once everything kind of cleans up, we end up with minus 64th minus 32h squared plus 40h all over h. And what can we do? We can go ahead and notice that each term in the numerator has a common factor of h. So let's go ahead and pull that common factor out. So we factor that common factor of h, and now we can say that these two h's divide out. And so we're left then with minus 64t minus 32h plus 40. And so now we've come up with a formula that will give the general average velocity of this ball over any arbitrary time period. So we just came up with a way of always being able to compute the slope of this line. So the slope of this line will always come out to be this expression right here. So that's it for an introduction to the difference quotient. We're going to get lots more practice with this. But in the meantime, I'm going to have you try to mimic this exact same example with just a slightly different function.